Okay, good morning, guys. Can you guys hear me? Somebody open their mic and let me hear how my audio is. Can you guys hear me okay?
I can hear you fine, Professor.
Wait a minute. Okay, can somebody say something? I need to adjust my audio for you guys.
I can hear you fine.
Okay, perfect. Thank you. All right, let me see how many people are joined in. Let's see here. Okay, I think we're good to go. All right. So I have a list of terms I want to go through before we start to do some exercises. I want to apply the K map. You guys practice using K map. You did a quiz, so we're going to apply it to a problem, and then we'll do some practical problems. Probably start next class. So if you had a chance to print that document off a blackboard that's dated for today, have that out. If not, I want to give you a second to print it out if you have the capability to print. If not, just write down what I have on the board. This probably is the most important document from the lecture from last week. So if you can get through this, I think the rest of the material we need to go through should be pretty simple. So I'm going to start by defining these terms and then show you how we apply a K-map to this. And then, like I said, we'll do a practical problem later on. Now I have this list. I want to start with the third one, a literal. A literal is just a letter of the alphabet used to represent either the input or output of a logic gate. So we've already used literals. We used, for example, the A, B, the X, those are literals. So literal is just a letter of the alphabet used to represent the input or output of a logic function. A variable is a literal with no complement or no bar over it. A complement is a variable that has a bar over it. So in other words, if I have A, that's a variable. If I have A bar, you say not A or A not, then that's the complement of the variable. But both of these are literals. So this is a variable, this is the complement of the variable. The two together, I can refer to those as a literal. So A is a literal and not A is a literal. So you want to know what a literal is, variable, and a complement. Then you have a sum term. So I'm going to erase these to make some room as we go. So again, a variable. So I might have variable B. If I take the B and I put a bar over it, then I have a complement of the variable. So that's B not or not B. And the literal could refer to either one of these, either A or not B, or B or not A. I'm sorry, B or not B is what I'm trying to say. So variable, complement, and literal. Now a sum term, what was we equate summing with oring? So it's a sum term. Let's say I have some literals. I got A and maybe B or B not or something like that. So a sum term is when I put the cross in between the two literals, and so you read that, you guys recognize that to be or. So oring and the sum term basically represent the same thing. You can think of oring as oring these sum terms. So we like to think of oring as summing. And I can show you why using a truth table, but I don't want to use up our time right now doing that. So a sum term, basically this is oring. A product term, I take this and put a dot in between them like that. So you recognize that as an and. Now remember, I can write this just like this. I can say A. I can omit the dot and just write A. And it's understood to mean and. So an and term is the same as a product term. So we think of anding as a binary multiplication. We think of oring as a binary addition and anding as a binary multiplication. So sum term and product term. Now what's important is this idea of a sum of products. So we'll talk about a sum of products and a product of sums. So a sum of products, I got this product term and I got this product term. If I put a or between these, then I have a sum of products, an SOP. Or I might have a product, I might have something like A, B, C, and let's do it this way. A, B, C, D. So that would be a product of sums. Now what's important for us actually is the SOP. Because when you guys write a program with the PLC, you're really writing a really long SOP. So we're going to focus on the SOP. But one thing I want you to remember is that just write this down somewhere, and it probably won't make a lot of sense right now, but it'll make a sense in a second. So anytime I have an SOP, a sum of products, they always evaluate to 1. Just as a rule, SOPs evaluate to 1, a POS evaluates to 0. So this is just a rule. Write that down. And again, this is the one that has application for what we do in this class. So SOPs evaluate to 1, POSs will evaluate to 0 by definition. So term, sum of products, product of sums. Again, the most important one is the SOP form. So what I have here is I have a circuit, a logic circuit. And of course, you can represent this circuit several ways. Here's represented as gates. But if I write the expression, this is the Boolean expression for this circuit. And you can see that this is a sum of products. And if you wanted to, you can write this using your ladder logic. You can write this, you can implement this using ladder logic. So again, when you write ladder logic, and really what you're dealing with is a PLC program is it's a really long SOP. So if you have the handout out, I have a little note at the bottom of the handout. This is true for SOPs. You're allowed to have this. You're allowed to have this when you have a SOP. You're allowed to have that, but you're not allowed to use this one. So this is okay. This is not okay. The reason this is okay is because I can actually implement this in ladder logic. I mean, it would be pretty easy if I have a gate and I want to implement this. I can just put bubbles here to get the knots, and my variable A, B, C, and X is like that. But to get this one, what I would have to do is A, B, C, the bubble will go here. So these two are different. They're not logically equal. And I actually showed this when we were together in class. I showed you that A, B, not is not the same as A, B, not separately like that. I proved that to you using the truth table. So the point I'm making here is that when we use this SOP form, which I'm getting into right now, we're allowed to have this, but we're not allowed to have this. This I can implement in a PLC program. I mean, it's pretty easy. I can just take A, I want to AND these. I can AND them. Since that's an AND and not an OR, but I can go A, B, C, and I can not these. But how do you implement this one? There's no way to implement that because you can't not the output. So given something like this, what you would do is, if you remember, break the line, change the sign. Given something like this in a problem, you would actually demorganize that. So you would break the line and change the sign. So to get rid of this, given this, and there will be, I think, an example coming up where I actually show this. I'll give you a solid bar over variables. All you got to do is demorganize it. So this would become that. Okay, so again, this is not allowed, but if I have individual bars over each variable, that's allowed. We'll come back to that, so don't really worry about that too much right now. I'm just kind of throwing a lot of stuff at you. We'll piece it together and it'll start to make sense. All right, so now what's important here is a standard SOP. A standard SOP. Here's an example of an SOP. This is a non-standard SOP. Now let me explain what I mean by that. One of the terms, I don't think I had it on there, it may be on your sheet, domain. Domain. So add that to your list of variables if I don't have it on the sheet. I don't have the sheet in front of me right now, so I might have left that off. But this actually is important. The domain is a list of the uncomplimented literals in a Boolean expression. The domain is a list of the uncomplimented literals in an expression, so a list of the variables. So like for this one, let's say I change that to a not. I'm going to put a not in there. The domain, I'll just put a D here for domain. The domain would be, so I got an A, I got a B, I got a C, I got a D. That D is knotted, but I don't have to show the knot over here when I list the variables. I don't have to show it as a complement. So the domain here for this expression is A, B, C, D. Well, what makes this a non-standard SOP is a standard SOP, every member of the domain would appear in each term. That makes it standard. Every member of the domain would appear in each term to make it standard. Well, this one is missing, it's missing C and D. This one is missing the A. And this one is missing the B and the D. So this is a non-standard SOP. So the first thing you got to be able to do is turn a non-standard SOP to a standard SOP. So I want to show you how to do that. And to do that is actually quite easy. Let me see what I want to use as an example. So I want you to think about something. So if you don't have the handout in front of you, write this down, this expression. All right, so here's an expression. Now, what I want to show you is, think about this. Let's say I have two variables and I OR them together. I'm going to OR a variable with this complement. If I have A or A not, if I OR them together, and somebody tell me what that's equal to. What's the logical evaluation of this? What is this equal to? A, if I OR A with this complement, what would I get? Anybody? If I OR A with its complement. No takers? If I OR A with this complement, I get a 1. I have to get a 1, right? Because all A is allowed to be is a 0 or a 1. And if I choose A to be a 0, say I choose A to be 0, that means not A has to be 1. And I have a 0 or 1, that's a 1. Or if I choose A the other way, let's say I chose A to be a 1, that means the complement of A has to be a 0. So again, I get a 1. Anytime I OR a 1 in anything, I get a 1. So this turns out to be very important. Anytime I OR a variable with its complement, I get a 1. And just like in regular algebra, when you multiply by 1, you don't change the value of it. Well, when I'm using Boolean algebra, when I OR a variable with its complement, I get a 1. And if I add anything with a 1, it doesn't change the logical value of it. It's like multiplying by 1. So what I'm saying is, what you can do is this. I want to change this SOP from a non-standard SOP to a standard SOP. I can see this is a non-standard SOP because I'm missing letters from the domain for certain terms. So let's first list out the domain. Domain for this expression, well, I'll give you a second. You go ahead and list it out on your paper if you're writing this down. The domain, if you write it down, I got an A, I got a B. Again, even though the B is knotted, I show the variable, not the complement. So I got an A, I got a B, I got a C, and this one has a D in it. So there's my domain for this expression. I can see it's non-standard because this one's missing D, this one's missing C and D, and this one's okay. I have all the members of the domain in this term, so that one's okay. But these two make this non-standard. So what I got to do to change this to a standard SOP is some kind of way I got to get a D in there. I got to get a D in there. And the way we're going to get the D in there is by using this idea. We're going to AND this term with the thing that's missing in this complement. So I'm saying is what we're going to do is we'll take this term, I'm missing a D, so I'm going to AND it with D or D naught. And I'm allowed to do that because if I, basically a D or D naught is a 1, and by ANDing or multiplying variables by 1, I don't change the logical value of it. So I'm going to multiply 1 by 1, not like this, but like this. I'm taking the variable in this complement. So by ANDing this term with D or D naught, then I don't change the logical value of it. So now you would distribute that. That's called expanding the term. So you go ahead and expand the term, and if you expand the term, what you get is A, B, C, D, or taking this into there, A, B, C, D. The B is knotted, and in one of those, the D would be knotted. So basically, if you distribute into the parentheses, you get this. So what I've done is I've taken this term right here and I expanded it. Now, if you were to write a truth table for this, I can substitute now this expansion for that term right there. What I get is a bigger SOP, but what I'm doing is forcing this thing to be non-standard, or forcing it to be standard. So what I want you to do is to go ahead and make this term a standard term. Now, when you do it, you're going to OR it with, obviously we're missing a C and a D. Do it one at a time. OR it with C and C naught, and then take those two and expand it by ORing with D and D naught. And you'll expand it. Take your time and do it. Don't try to do the two variables together. And when you do that, I'm going to write the new. So right here, I'm going to take this, and that goes in place of this. And you go ahead and expand that term, and then we'll do it together. All right, so I'm going to expand this one. Again, we'll just do it one variable at a time. So I got A, B, bar, bar. First thing I'm going to do is add a C by ORing this with C or C naught. So I got C or C naught. And I get A, B, C when I distribute in, or A, B, C. Both of these are knotted, and for one of these I get a C naught. So when I expand this with my C, I get this, and then I'll do each one of these individually. This time I'm going to add D to the mix. So for this one, I get A, B, C. I'm going to OR that with D or D naught. And then I get A, B, C. And I'll OR that with D or D naught. So if you're working along with me, go ahead and work this out. So I think when you expand it, here's what I got. So compared to what you got. And so what I'm going to do is try to write the whole thing up on the board here. So for my first expansion, I got this. I got A, B, C, D. This is knotted. From this, I got A, B, C, D. That's knotted and that's knotted. That takes care of the first one. And then from this one, I got A, B, C, D, not, or A, B, C, D, not. That takes care of that one. And then I got A, B, C, D. Those are all knotted. And then I'll squeeze this one in. I got A, B, C, D. And these are all knotted. Now, if I have A or A, that's equal to basically A. There's another one of the rules. If I OR something with itself, I get the thing that I'm ORing. So if this is a 1 or a 1, that's a 1. If this is a 0 or a 0, that's a 0. So that from this, that says if I have anything repeated, it basically is that thing. If I OR something with itself, then I get that same thing back. So what I'm going to do is I can apply that to this and see if I have anything repeated. So do I have anything that I'm writing twice? I don't think that I do. I got that one. Yeah, but if I had, let's say, this term repeated, and that came up a second time, then because of this, I can just get rid of that. So I want the fewest number of expanded terms that I can get. So hopefully you guys followed that. If you didn't, go back when I put this on YouTube and rewatch it. You got to be able to change a non-standard SOP to a standard SOP by using their rule. And if I have a variable or with itself, it has a logical value of 1. And by ANDing anything with a 1, it doesn't change the logical value of it. So we can use that to expand any non-standard SOP to a standard SOP. That's the first step. Once you're able to do
Aren't you missing a term at the end of that equation? Isn't there supposed to be an A, B, C, D without any knots on it?
No, I didn't get that. I don't think I got that. Was that an original equation you thinking?
Yeah, that's what you wrote down originally. Did A, B naught
I think
plus
originally,
C
let's not
naught
make a
naught
mistake.
plus D.
I think I started with this. Since this is what you have, I started with A, B, C naught, or A, B naught naught, or A, B, C, D. I should have had that knot. Did I have that? Was this unknotted or did I have it without the bar?
You had it noted.
There was a bar there?
Yes.
Okay. Okay, well, go back. I think if you look at the YouTube, you'll see, even if I left it off, it's okay. As long as you got the technique, we're good to go. So is everybody okay with that, what I've done so far? Okay, I'll take your silence as a yes. So if you see how to do that, the next thing you got to be able to do is write the binary value for each term. Now, it's really simple to do. Now, don't worry about what we're doing yet. Don't worry about why we're doing this. Just do it, and then it'll make sense later when we put it together. Once you get this as a standard SOP, then each term has a binary value. Each term has a binary value. And all you do is a variable with no bar on it, you write a 1 for it. A variable with a bar on it, which makes it a complement. Any complement is a 0. So what I'm saying is this. If I write the binary value of this term, it would be 1, 0, 1, 1. A 1 because I have a variable here and a 0 for any complement. 1, 0, 1, 1. That's the binary value of that term. The binary value of this term would be 1, 0, 1, 0. This would be 0, 0, 1, 1. This would be 0, 0, 1, 0. This would be 0, 0, 0, 1. And these, I don't know if you can see that, but what I have is A, B, C, D, and they all have bars. So that'll be a 0, 0, 0, 0. So if I ask for the binary value of a term, if I have a variable, that's equivalent to a 1. If I have a complement, that's equivalent to a 0. Replace the variables with 1s and the complements with 0s, and you got it. Okay? Everybody, so far, so good for everybody?
You still need the last term on there still.
Okay, on the,
The just not D term. The ABC not D.
okay. So you're saying I left off the last part of this part right here. So I have to order that with A, B, C, D naught. Thank you. And then I will set that equal to X. Okay, so if you look at the handout on Blackboard or whenever you go to Blackboard, there's another one like this, problem number 3, where you can go through and you can do this just to practice. I want you to practice this. And what I'll do is I'll put the solution up for it to make sure you get the same thing that I got. So we'll do that. Try it before next class. If you have the handout in front of you, you can look at number 3. You see what I'm saying? I use W, X, and Y, and Z for that. But you can, it's the same thing. So try to do that one and for practice. And then I want to do 1, 2, and 4 off the sheet. And again, if you don't have it, the sheet in front of you, I'll put it on the board here. Okay, so problem number 1, they give you this. Let's say I got A or B or C or D, and these are knotted. And this is a product of sums. And so we say at the beginning of this, a product of sums always evaluate to a 0. That's problem number 1. If you look at problem number 2, they give you A, B, C, D, and the B and the D are knotted. So this is a sum of products. Here I just have one product. So, but the point is, given this always evaluates to a 1. So by definition, POSs evaluate to a 0, SOPs evaluate to a 1. So anytime I'm ORing things together, but OR together is going to evaluate to a 0. If I add these terms together, they're going to evaluate to a 1. So the question is, what is the value of A, B, C, and D to make this first statement true? And what's the value of A, B, C, and D to make the second statement true? You go ahead on your paper and write that down. And then we'll do the last one, which is actually what I want to get to. So how would I make this first statement true? Well, pretty simple. If I want to make the first statement true, if I'm ORing these together, the only way to get a 0 is this has to be a 0. B has to be a 1, and then when I knot it, it changes it to a 0. So this has to be, let me write out the solution like this. So A has to be a 0. B, not B not, but B is a 1. C is a 0. And D has to be a 1 to make this true. And then this was kind of the same way here. A, this time I want to get a 1, so that means everything here has to be a 1 because I'm ANDing. A would have to be a 1. B would have to be a 0 because I'm knotting it, and when I knot that, that changes that to a 1. C is a 1, and D is a 0. Now these are actually pretty easy to do because all you got to do for this one is what I did before. Just write the binary value for the term. You can write the binary value for the term for the letters that are unknotted. It's the way to think about it. Okay, so if I wrote the binary value for this, it would be 1, 0, 1, 0. That's what I'm saying, which is what we got for a solution. Now, everybody look at that last problem, because that's actually what we got to do the next step of this stuff that we're doing. And what I'm going to do is, I guess Wednesday, we'll put all this together, and then you'll see how we apply this to the PLC. So look at that last problem. They give you a standard SOP. They give you a standard SOP, and they want you to, let's see. They want you to write the truth table for that standard SOP. So what they give you is this. We'll set that equal to some variable x. And I want you to get the truth table for this. So all you got to do is, the first thing you'll do is write the binary value for each term. Well, that's easy to do. This is 0, 0, 1. This is a 1, 0, 0. And this is a 1, 1, 1. So the first step to getting the truth table for this is write the binary value for each term. The second step is you draw your truth table. So draw your truth table at 3 variables. With 3 variables, the number of rows in the truth table is 2 to the nth power, where n is the number of variables. So I got 3 variables. I'm going to need 8 rows. So I'm going to make this a little higher. we'll put these binary values on top so I can make it higher. So this is 0, 0, 1, 1, 0, 0, 1, 1, 1. And then I'll make my truth table. You go ahead and see if you can remember how to do the truth table. There was a certain way I told you to number it. I have A, B, C, and X is my output. So what we'll do is the first row we'll start counting. We're counting in binary is what we're doing. So it'll be 0, 0, 0. So I start like that. And then what I do is the one right here, the one closest to my output variable, I'll alternate every other bit for the 8 rows. So what I'm saying is this is 0. So I got 0, 1, 0, 1, 0, 1, 0, 1. 1, 2, 3, 4, 5, 6, 7, 8. I got 8 rows. So I alternate every bit, 0, 1, 0, 1 for the first one. The next column I alternate every 2 bits. So 0, 0, 1, 1, 0, 0, 1, 1. The next one is we skip, this is all power of 2s. So it's not every 3, it'll be every 4 bits. This would be 0, 0, 0, 0, 1, 1, 1, 1. You want to make sure you put your truth tables in this order. If not, then your solutions will disagree with my solutions, and that'll be a problem. So I'm going to put my bar here, and by doing it that way, what you get is all the possible combinations for A, B, and C. You're guaranteed to get it if you do it the way I just showed you. Now, all you got to do, once you get your truth table, is the binary value of each term. Since this is a SOP, SOPs always evaluate to 1. So what that means is the binary value of this term here is pointing to a particular row in the truth table where 1 occurs in the truth table. So this binary value for this one was a 001. So I go to 001 here, and I'll put a 1 there. That means there's a 1 at that row in the truth table. There's a 1 right there. Where this condition is true, where A is barred, B is barred, C is unbarred, there's a 1 there for that to be true. Here, 1, 0, 0, 1, 0, 0 is right here. There's a 1 there. 1, 1, 1, we're all 1s. There's a 1 there. And every space you see here, every space is a 0. I can put the zeros in there, but I'm not going to do that because I don't want to make this too cluttered. So once what I'll do is I'll walk in here and I'll give you an SOP non-standard. So then what you'll do is you'll make it a standard SOP by the method I just showed you a few minutes ago. So you'll take the non-standard, you'll turn it into a standard SOP. Then you'll write the binary value for each term of the standard SOP. And then you'll draw the truth table, and whatever the binary value is for a term, that's where you'll put a 1. Now, if I wanted to, I could show, I didn't ask you to do this, but you can show the value of a row using literals. So what I'm saying is, this row right here is A, B, C. Well, A has a value of 0, B has a value of 0, C has a value of 0. That means these are all not. Now, what that gives you is this. If you remember, we said SOPs evaluate to 1 and POSs evaluate to 0. So any place you see a 1, if I want to get the SOP from this, all I got to do, if I want to get the SOP, all I got to do is write my variables. I'm going to get this thing back. This is A, B, C. I got a 1 here. This is A, B, C. This is A, B, C. I got 2 zeros here, so that's bar. That's that one. I got 2 zeros here, so that's a bar. That's that one, and so forth. And then what I would do is I would order these together to get this equation back. Well, likewise, if you wanted to find the POS from this, you would do the opposite. Now, POS we really don't use that for the PLC. But I just want to show you, if you want to get the POS, if I wanted to get the POS for this truth table, I do the same thing. I go A, B, C, we'll just do a couple terms. These are all zeros, so that would be bar, bar, bar. And this would be, this one would be A, B, C. I got a 0, 0, so bar, bar. And I would do that for every space. But then what I would do is I go A, cross B, cross C. They're all knotted. And then I would end it A or B or C, and I got a knot here, and I will keep going. So this would be my POS for that truth table. Again, don't worry too much about that. I'm just showing you can get the POS from the truth table pretty easy. What we're worried about though is the SOP. That's what's important. So if you understood everything that I said today, then you're in good shape for next class. We'll take this, we'll actually solve a problem with it. If you're not okay, go back. I'll put this up on YouTube between today and tomorrow. Go back and rewatch this and follow it. Make sure you can see what we're doing. And in the meantime, I want you to, on the bottom of the sheet that's on Blackboard for today's class, we worked all the practice problems except for number 3. I was going to give it to you for homework, but I got enough stuff to grade. But I want you to go ahead and do it. I won't know if you did it or not, but go ahead and do it just for your own personal satisfaction. And make sure you can expand number 3. And I'll work it out, and I'll put the solution up some kind of way on Blackboard. Just make sure you're doing it the right way. You should be able to expand it, and you should be able to write the truth table for number 3. So see if you can do that, and then we'll talk about it on Wednesday. Anybody have any questions for me before I end the session? Okay, then you guys have a great rest of the day. And again, stay safe. They say this week's supposed to be a bad week. Things are supposed to spike out there as far as this virus thing is concerned. So I know you guys are taking care of yourself. Keep doing that. And I will see you on Wednesday, same time.